Last one for today and for the rest of the conference. My name is Jiri Pechanec. I work for Red Hat, and I'm here to speak to you about the project I'm working on, and it's an open source project called Debezium. So, what are we going to talk about today? First of all, we will discuss what is change data capture, what are the principles behind it, and what are the use cases for change data capture and streaming of change data. Then we will discuss different methods how to create change data stream, and we will discuss their advantages and disadvantages. And then we will move to the core of this presentation, to this talk, and that's what does it mean, this term, this expression? Well, I guess if you know Kafka, you have already heard about the concept or the principle of duality between log and database. That we can express database as a log of events, and a log of events can be materialized into a database. So effectively, change data capture is something like turning the database back into the stream of changes, stream of events that describes every single change, both in data and schema of the database over the time the database is monitored. What are typical use cases for change data capture? Well, there are multiple of them. I would say the most simple is probably the data replication. We have a database that is our single source of truth. It's a legacy database to which our enterprise application is connected, and we need to replicate the data from this database to other systems. Those systems can be just another database. So we can think about it like replication from, for example, MySQL to Postgres, which is something that can't be done directly. Or we can read our data and feed those data into downstream warehouse or analytical systems for further processing, for deep learning and similar stuff. And also one of the options is to use this approach to share the data we have in the database and we are creating with other teams. But we want to share them in that way that we don't want to have tight coupling between the teams, so we extract the data as a stream and share the data to other teams as this stream. The next use case is, and I would say it's quite popular these days, it's usage in microservice architectures. Well, we know that in microservices, one golden rule is that every microservice should have its own data store, where it stores its own private data, and those data are not data, but this store is not shared between multiple services to create tight coupling. But somehow we need to share the data because, well, let's say one of the microservice is user management, one of the microservices accounting, and we need to send the data or to replicate the data from one microservice to another. So we can use change data capture as a way how to share the data between those services, and we would share those data using loose coupling. And this, of course, will allow us that every service, as it will read the data, will receive the stream, it will store it into its own repository, to its own data store, and it can optimize their view on the data according to its needs. So it will not use the stream as the raw stream, but will convert it to its view, for example, to graph database. And then there is the rest of use cases. I would say these are just supplementary cases. So first of all, usually when we are using databases to improve the performance, we are putting a cache in front of the database. The problem with caches is that we need to update them or invalidate according to the changes in the database. So, using change data capture stream, we can ensure that the changes are immediately propagated to the cache, and the cache is kept in sync with the database or data store behind. The next supplementary case is support for full text searching. If you are storing data in database, you frequently need to support full text searching over those data, but not all databases are optimized for this scenario. For this case, you usually deploy a solution or a solution like Elasticsearch or SOAR, where you store the data and you are running full text searches over those data. So you can use the change data stream to keep this full text index in Elasticsearch, for example, to keep it again up to date and synchronized with the data stored in the database. And the last but not least is again one of the modern principles of architecture of application development is using command query responsibility separation, where you have an input of commands that somehow modifies the internal state of the application, and you have a model of this that models or that represents the state of the application that is read and presented outside to the application. So you can use change data capture and the stream as an input to the command input to CQRS application. So now we have already discussed what is change data capture and for what we can use, but how can we capture the changes? That's very complex and difficult questions. There are multiple approaches, let's say simple and more complex. So let's start with, I would say, that the brute force approach. So your application would execute dual writes. So you will write a change into the database, then you will write a change to the cache, then you will write change to the index. So typically, it definitely bloats your code. You have to be careful with failure handling, because what happens if you update two of the resources and the third one is not? You don't have distributed transactions available for this scenario, so you are on your own. And also, this solution is quite prone to race conditions. Yeah, because you issue a command to update database, you issue a command to update a cache, but if you are not using synchronous approach, then you can't guarantee the order in which the change will be present in each system, which can lead to quite interesting phantom bugs. So, okay, let's move to, I would say, more sophisticated solution. So we have a database, and we will build an application that will poll the tables of the database and will publish the content of the tables as a stream. This would work, but it has its own drawbacks as well. First of all, how would you detect that a row has been changed? Because if you would like to detect this, it's easy to find a new row, but how do you identify the updated row? Then you would need to keep a separate copy of every row, and you had to compare them and to verify if there is a change, which is definitely not viable for larger data sets. How would you handle deleted rows? Again, if somebody deletes a row from the database, you need to have a separate list of the data, separate list somewhere that would allow you to detect missing records, so you can create, issue a delete row event. So again, it's quite not feasible and definitely not scalable. One of the approaches could be triggers. Yeah. In this case, you would have a store procedures that would be issued when a change is created, is done on the table, and your stored procedures would do something. This can work, but the problem is that using stored procedures and triggers have its own drawbacks as well. There can be performance issues. There is definitely problem with versioning the code of stored procedures and similar stuff. So let's look at how we believe it should be done, how it should be done correctly and non-intrusively. When we would like to detect the changes in the database, we would read the database log. Database log contains records of all changes made to the database. Whenever you are writing a transaction to the database, the database record is created in the database log. Then, when you issue a commit, the change in the log is persisted, and only after that the content of the database is modified. So we have everything we need. We have in the log. What will happen if your log reader will fail? Well, in fact, nothing happens, because when you restart it after a couple of minutes, you will lose no data, because everything is in the log, and you will just restart the reading of the log from the last position that you have processed. So it's pretty easy and pretty robust. And last but not least, using this way, this is transparent solution to upstream applications, because they don't need to know anything about solution that creates and generates the change stream of events. So, what are the database logs? I've already mentioned that every write to the database goes first to the database log, and only after the change is committed, the data structures that represent tables are updated. The logs are used mainly for recovery in the case of database crash, and also serve as a source for cross database instance replication. In case of MySQL, we are calling this structure, or this log is called bin log. For PostgreSQL, it's a write-ahead log. In case of Oracle, it's redo log. So, but the principles are the same, and MongoDB is using the name oplog, operation log. But again, the principle is the same. We have ordered sequence of all changes made on the database, on the data source. So let's use this let's use these database logs as a source for change data capture. Well, we know from where we get the changes, but where we should put those changes. We have decided to use Apache Kafka as a target or as a target storage for those changes. Because Kafka is by itself very well suited for change data capture streams. Why is that? Every message that goes to the Kafka have a key. So we can uniquely identify change in the database by its primary key and associate it with a message key in Kafka. We have guaranteed ordering in Kafka, which is very important. We have to keep the order of messages as were written to the database log, and those should be passed downstream in the same order. There is, of course, a certain limitation that ordering is guaranteed only per partition, but this is something that the application has to be prepared to handle. And if you use primary key of the entity as something that defines the partition, you have guaranteed that all events that relate to a single entity ends up in the same partition and in the correct order. Also, what is quite interesting that Kafka supports compaction. Compaction. Don't know how many of you are aware of all Kafka functionality, but compaction is a very useful feature in case you are using Kafka not only as a message bus, but also as a storage. What is it, the compaction? Compaction says that the source of the messages can send a special message that says, I am removing all the messages that have this or my primary key. And when Kafka is rotating its logs, it automatically compacts them and remove all obsolete messages that were related to this deleted entity. And of course, last but not least, Kafka was built and is sold as extremely horizontally scaled solution. So when you have large database, it's not a problem to stream large number of events from that to the Kafka and store it there. Now we know where we store the data. How we develop the reader. Kafka has a framework called Kafka Connect that serves as a basis, as a framework, as a runtime for a developer to develop connectors that either read data from outside sources and write them to the Kafka. These are source connectors. Or if I want to export the data, the events messages from Kafka to external system, you would write a sync connector. Kafka Connect is runtime. You are registering your plugin, and it manages its life cycle. It guarantees, in case of cluster deployment, it guarantees proper balancing of the load across the cluster and similar stuff. Kafka Connect also provides us a feature. It's tracking of offsets. What is it offset in this context? Offset is a unique identifier of the source data that is sent to the Kafka. So in our case, it's a position in the database log associated with the message we are sending to the connect. Why is it important? In case there is a crash on a Kafka on connect side or our solution side, then when Kafka is restarting the plugin when it's restarting the plugin, it will get the recent offset that has stored, and you can restart the reading from the proper position in the database log. Also, what is important is support for schema, because the data coming from database are somehow structured. Yeah, because it's table consists of rows consist of fields, and fields are of some type. So we need to keep this information, this metadata, and that's for schema support is. Also, I've already mentioned clustering, and last but not least, the Connect is already, I would say, is quite popular, and there is a huge ecosystem of connectors already available. So, how change data capture topology looks like with Kafka Connect. So, on the first slide, we have a Kafka, and we have two data sources, MySQL and Postgres. So, we need Kafka Connect on the input to get the data to the Kafka, and Connect instance on the output to get the data out to the system that consume them. Now we see, and that's why I'm here, we see two connectors, two Debezium connectors, one that is able to read MySQL changes, and the other one that is able to read PostgreSQL changes. So those connectors are processing database logs, converts the messages, and stores them into the Kafka. And on the output side, let's suppose that we have Elasticsearch as a destination system. So we would use Confluence Elasticsearch connector to process the messages that Debezium has created, and the data are then written to the Elasticsearch. So the data in database and full text index in Elasticsearch is kept in sync. On the output side, you don't need always use Kafka Connect, because the data are available also via plain Kafka consumer API. So you can have, for example, Apache Camel integration application or Applix Vertex application that are reading the data from Kafka using consumer API and forwarding them to our enterprise system. So I've been talking about messages created by Debezium. So what is their structure? Well, the message is in fact a pair of key, which is a primary key of the table, and that's reverse engineered from the database metadata, and the value of the message. The value is the payload. What is the payload? Payload contains three different components. The first one is before state. Before state contains the data as were stored in the database before the change has been applied. So in case of insert, before would be null. In case of update, before would contain the data before we have overwritten it with updated data. Then there is after, which contains data after the update, so the actual data. And then there is a source info that contains metadata about position in the database log from where we have received the change. This is the logical structure of the message. The message itself can be serialized into two formats. The first one is JSON with its own advantages and disadvantages. It's human readable. Everybody likes it. The problem is that it's quite verbose. What is quite important that you can have a schema included in JSON. This is optional feature. You can send either plain JSON without schemas, and then it's up to your clients somehow to know what format they should expect, or the schema is coming embedded in the JSON, so the clients can look at the schema and they know in what format what data types are coming in those before and after before and after fields. The second option is using Avro converter. Avro is Apache Avro project. This allows us to convert the message into very efficient, compact, and small binary representation that also is somehow related to the schema. The disadvantage in this case, or small disadvantage, is that to use this approach, you need to deploy also Confluent schema registry that serves as a storage for the schema, and every Avro message created by Debezium contains an identifier to this schema stored in schema registry. Well, initial snapshots. We have been discussing that we are reading the database logs, but the database you want to stream may run already days, weeks, years. And in this case, the database logs will definitely not be present because they are typically periodically removed as a part of database maintenance. So, how to solve this constraint? We could either stream just the new changes, but then it wouldn't make sense for certain applications not to know about all data, or we can use so-called initial snapshot. In this case, when we start the corrector for the first time, it will look at the database, then it will takes the snapshot of all tables, or all tables that we are monitoring, of all tables, will send a huge set of create or insert events into the Kafka, and after that, when this consistent snapshot is completed, the connector will switch to the database log monitoring and will continue using the approach we have been discussing before. So, which connectors are offered by Debezium? Right now, we are supporting, or we are providing free connectors. Historically, the oldest one was MySQL, or is MySQL. Then came Postgres. Next came MongoDB, which is a little bit specific because it uses a different format from the databases, given the limitations of Oplog. We have prepared Oracle plugin, which is, we have a PR completed for that. It goes through the final round of review and will be merged to the next version. And for the next, it depends what will be the requests of community. We might think about SQL Server, MariaDB, Cassandra. I have been asked also for DB2. So in this case, it just depends on what will be the most requested, the most popular data source. In our connectors, we are trying to be as much consistent as possible. We try to use the same format for the messages across all connectors. So the clients won't need to be prepared to handle different formats. We aim to keep the common configuration option across the old connectors, again, to have to provide a consistent experience. And we are definitely not forgetting about monitoring, about production. So we are exporting a set of JMX beans that contains important metrics for our scenario. So it's when you are doing snapshot, you see how far the snapshot has progressed. You can monitor how far behind you are the master. So you can detect spikes, or you can detect the situations when the downstream processing has somehow stalled, and you need to take an action, and so on and so on. How the connector is operated? Kafka Connect is usually configured via REST API. So, using REST API, you will configure or set up the connector. You can control the life cycle, so you can stop the connector, suspend, resume. You can reconfigure the connector or update to a new version, or you can start it again from scratch. And if it's necessary, you can retake the snapshot if needed, because there was a data loss or something like that. So now let's start with demo. So I have here a Java EE application that is connected to MySQL server, and I will monitor this database to catch the events or changes created by this application. So this is the MySQL, and this is the application. So let's look at the application. It's just plain Java application that serves for tracking of hikes. If you like hikes, you can record the hike that you made from, to, and so on. So how it you can see, you can filter the hike, you can add a new hike, yeah. Well, just plain application. So first of all, what we need to do is to register, or sorry, to start Debezium together with Kafka and the rest of the ecosystem. To simplify the things, I have prepared a set of Docker Compose files that takes care of all necessary dependencies. So, if you look now, we can see that there are definitely way more processes running. So we have a Kafka, we have schema registry, we have Zookeeper that is required by Kafka, and yeah, and we have Debezium Connect. We have a Connect instance that we will configure to start our plugin. So first of all, what we need to do is register a new plugin. So I have prepared a command for it. So as I mentioned, it's a REST call. So I have registered a MySQL plugin. You can see the connector class is MySQL. host name, port, user, password, so the connection data, then server ID, which is the number under which the plugin registers to the database, and the rest is probably not important. So first of all, let's look what is the status of the connector. Again, we are using REST API, so we see there is an inventory connector that is running, and it runs one task, again, that is running with this ID. So let's try to create, or not yet, let's look into the Kafka topic. And we can see that the Kafka topic already contains some data. Why is that? That's because the connector has started with the snapshot. So the data that were already stored in the application were converted into the messages and were sent to Kafka. So let's try to create a new hike. So I came from Brno to Riga. Let's say, and I went via Prague. So I have created 2 records, and now you can see that there are 2 new messages. Is it visible, or should I increase the font? It's okay. So you can see the ID 5, the primary key with number 5. I have destination Riga, start Brno. ID 6, start Brno, destination Prague. Let's suppose that I will rename the Prague to Praha, because it's in Czech it's Praha. And if you look, we see that there is a new event. This new event contains before with Prague and Brno, and now it contains after with Praha and Brno. So this is an update event that contains the original data and the new data. Now what will happen if we remove one of the hikes? Well, there are 2 new events for the same ID. The first one is delete event, again that contains the original data, and the next one is so-called tombstone. And that's exactly the special marker that says to Kafka that when you are doing compaction, you can remove all messages that have key ID with value 6. Yeah, and now I've been also mentioning schema. So I have via REST I have queried schema registry, and here you can see the schema of the data we have been sending. So these are metadata. So here is table. I can't see it. Sorry. I just managed to lose myself. Never mind. Let's move forward. So let's go back to the presentation. The next topic and next functionality provided by Debezium are message transformations. When you have messages stored in Kafka, you need somehow, or frequently you need to modify them. You need to extract part of the data, you need to convert them to different format, you need to route them to different topics, to enrich them, or whatever. For this, you can use Kafka Streams framework, or Kafka provides a simplified version, so-called SMT, single message transform. That's a piece of Java code that is applied on every message that comes to Kafka or is coming out from the Kafka. So you can modify the message according to your needs before it's written to Kafka or after it goes out. Debezium by default provides 3 different transformations. The first one is logical table router, which is useful in case you have sharded table. If you have a data set that is too huge to be stored in a table, in a single table, you frequently shard the data set to multiple tables. And in this case, Debezium would send the events to separate topics according to each shard. This logical table router will help you to send all shards to a single topic to keep the changes as a single stream. Next one is event flattening, or are event flattening SMTs. I have shown you the complex message structure we are using. The problem is that other sync connectors usually are not able to process with this complex structure. And they know only how to handle the after part. So we are providing SMT that is able to extract the after part, so you can apply it before you send the message to a downstream connector, for example, for writing to JDBC database, to database using JDBC. And now let's look at the other demo. And so we have seen how to source the events, and now let's write those events somewhere. Let's replicate our MySQL database to Postgres database. I have already started Postgres database, and so we are going to look at its content. So I'm going to execute a select, and you can see that table doesn't exist. Yeah. Well, we are not writing to the database yet. So the first thing we need to do is to register a sync connector. So again, we issue a REST call. A new connector has been started, and now let's try to do the same select again. And you can see that now the Postgres database contains exactly the same data as MySQL database. Just let's try to create again few new hikes. So from Brno to Helsinki. From Brno to Tallinn. And if we look, you can see that the Postgres database, that the new records were automatically replicated to the Postgres database, so both databases are kept in sync. And now let's say that I'm not going to Helsinki, but for example to Lviv. And if I issue the select again, then you can see that I have Lviv here instead of Helsinki. So again, I'm keeping the content of both databases in sync. Okay, we are short on time right now, so I will continue with the presentation, and maybe I will show you one more demo at the end. So, if you like Debezium, if you like what you have seen right now, you can try it for yourself. Go to our website, and we have a pretty extensive set of resources that will help you to start with Debezium as such. First of all, there is a very long tutorial that explains you all the components as you have seen right now, completely to detail. Then there is a quite extensive set of compose files that contains examples and let's say typical configuration and deployments for Debezium. Also, we are very friendly to OpenShift. So you can run Debezium on OpenShift. We have prepared scenario on learnopenshift.com. So if you don't want to install OpenShift and Debezium, you can go there and you can run the scenario online in Katacoda system. You can run it on your OpenShift. For Kafka deployment, we are using Streamzy project that deploys Kafka and Kafka Connect. And you can follow again instructions that are available on our website. So, what's in the future for Debezium? So, first of all, it's Debezium 0.8, which was originally planned to be released this week, but well, somehow Riga days have, let's say, we haven't managed it to on time because of me being here. The news in Debezium 0.8, we are moving to the latest Kafka, so Kafka 1.1. We will include the Oracle connector I've been already talking about, and we are also developing a reactive support for Debezium. You can run Debezium not only with Kafka, but also as an embedded solution inside your application, and you can skip Kafka and consume the events just in memory. We have an API for that, and we are extending this API with reactive support, so effectively creating reactive Debezium. For the future 0.x releases, we are going to replace existing MySQL parser right now. Again, there is already PR provided. We are using manual SQL parser. This new one is using Antler, so it's much more robust. Again, it's something that is completed and is waiting just for merging. We will definitely deliver more connectors. Also, we would like to provide support for InfiniSpan to act both as a sink and as a source. So we would have everything in place for the scenario of keeping database and cache in sync. And after that, when we release version 1, then the future is a little bit foggy. What we right now are thinking about is aggregation of events. So you would be able to aggregate the transaction events to a larger one, to aggregated format. And we would like to extend or provide building blocks for CQRS. Again, the scenario I was talking about at the beginning. So we are at the end. So what are the key points of today's talk? So Debezium is an open source project that brings change data capture for growing set of databases. Now we can say four databases already. It it works reliably in case of failures because there is loose coupling between source and sink, or source and destination. We don't have any dual write issues because we are using database log as a single source of truth. And of course, as it's open source project, we are welcoming every contribution that that you will throw at us. And just as a side note, Debezium is already run in production at multiple companies, multiple users, and we have already a user that is processing billions of events per day. So I think we can already say that Debezium is a battle tested.
And
resources.
We run out of time. Sorry. Yeah.
So just resources. You can find it. You can find all information in the presentation, and that's all. So thanks a lot for your attention, and enjoy the end of the conference.
Thank you very much. Unfortunately, we don't have time for QA. Just a quick information, we are waiting you in the room 3 for the closing session. There are going to be lottery and surprises, so we're really waiting you.